Copyright the University of Auckland. All rights reserved. The content and delivery of lectures in this course are protected by copyright. Material belonging to others may have been used in these lectures and copied by and solely for the educational purposes of the university under license. You may record the lectures for the purposes of private study or research, but you may not upload onto any third-party site, make a further copy, or sell, alter, or further reproduce or distribute any part of these lectures to any other person. Failure to comply with the terms of this warning may expose you to legal action for copyright infringement by the copyright owner and/or disciplinary action by the university.
Hello everyone, good to be back. So the first assignment is out. You have 2 weeks to do it, so you can do that. If it doesn't work, if something doesn't work, let me know, because I was just gonna go and say, hey, it's great. You can just click here. You can click on assignments. This first assignment, and there is a PDF with the instructions and the actual assignment. And a minute ago it didn't work, so so just try it a minute later, and now it works. So just in case you have issues, either try a little bit later, and if it still doesn't work, then send me an email, and maybe we can try. We can get another ways. So here's the assignment. You can just look at it. You can ask questions on Piazza if you have if you need some kind of clarification or anything like that. I've also added an R Markdown template, so if you want to, you can use it. So just to make it easier, it has essentially just all the set up. Let's see if this computer can open it. So you can open it with RStudio. Let's see if this will work. Even if you may not have RStudio assigned with it, you can just say open. So let's see if we can find it here. You don't have to use it. You can just use regular R files or text files, but just to make things easier. RStudio and file. Let me see if I can get it from downloads. So there it is. So this allows you. So essentially, it's just a template. You have to put your name here and agree to the statement here, and otherwise it just has templates where you can put your answers inside the code chunks. And then for those ones where I'm saying, you should run this, that it already has this commented out, so you want to remove the comment once you have put in your function and so on. I do just make it easier for grading as well as running, because then everything is in one. But again, it's not mandatory, but just should make it easier so you don't have to set up your own templates. All right, so that's the assignment. So let's go back to what we talked about last time. So last time we've been just looking at different examples. We've been doing a t-test by writing our own function to do it, doing summations, talking about a vector versus a loop operations. Just to recall from last time, in case this wasn't super clear, if you have a solution that uses a loop, the drawback is whatever you have inside the loop essentially gets executed every time you iterate, right? So that's the drawback. The benefit is that you don't have to store everything, and you can just reuse things. If you use vectorized operations, what it typically means is you kind of set up everything, and then you just do the operation, and you're done. So you don't have to evaluate a lot of things, but you will usually need to potentially create bigger constructs and then evaluate them. So that's the main two differences. So that's the trade-off between memory in one sense, so the one where you have to create first the big things and then run the computation means you need more memory. The one doing in the loop means you need less memory, but it may take longer if you do a lot of iterations. Just to be clear. So, all right. So let's go back to our examples. There's one more example that also illustrates the difference between the loop versus doing things in a vectorized fashion. So this is just a little simple example here that is a little more tricky than just summing up random things. So the idea is it sort of comes from poker, when you just want to detect. Let's say you have a sequence of cards, let's say, and you want to detect if they are 2 of a kind, 3 of a kind, and so on. For simplicity, let's just look at 3 cards, and we just essentially give them patterns like A, B, C, D, and so on. So we want to look at those and detect how many, of a kind are they. So, for example, for the first one, we would say there's on 1 of a kind because each card is different. In the second one, we're detecting, there's 2 are the same. The third one doesn't matter. And in the third case, we have all 3 of them are the same. And, this is just an example, but you could imagine them being in different positions in the card, right? So we want to write an R function that's named hands that essentially gives us exactly those results. So looks at the pattern and then gives us the result. Now the way we want to do that is we want to actually give it a full vector of all kinds of hands sort of attached to each other, and it's supposed to go through it and look at 3 adjacent ones and give us the result. Then look at the next 3 adjacent ones, give us the results, and so on. If we go through the vector and there is there are fewer than 3 entries left, then we just ignore it. That's the setup here. So let's say this is a practical example. So let's say I have this vector. The task is look at 3 entries, 3 elements at a time, and give the answer. So if we look here, we say 2, 1, 3. So that means all 3 are different. So it would be go to hand 1. So the case 1 where you made only 1. Second one has 2, 1, 2. So there are 2 2s. So it would go in the category of the second one of 2s. Then we have 3, 3, 3. So that's 3 of a kind. So it's of the third type. So far, and then we have here again, this is 2 of a kind. This one is 1 of a kind. It's 2 of a kind. And now we're left with 2 more entries, which is incomplete. So we'll discard those. And then the result is supposed to be the counts of how many of each type we encountered. So I was just saying the numbers, right? It would be 1, 2, 3, 2, 1, 2. And now we need the counts for those. So that's the result here. There's 3 of 2 of a kind, 1, 3 of a kind, and 2 of 1 of a kind. Okay? So we want to write a function that does that. So how we would go about this. So one way is essentially to just walk through it and just keep a count. So let's allocate a variable counts, and we just give them the names hand 1, 2, 3. And that's where we will be storing what we see. We will look at how many hands do we have in the vector just by taking an integer division. So regular division would give you a real number. Integer division has these percent divide percent, so an infix operator for integer division, and essentially just gives you the same, with the same result as if you could truncate length x divided by 3. So you get an integer. All right. So now we're going to loop from 1 through m. So for all the complete pairs, we're going to look at things. And so to do that, we can just pick the first element by simply saying 3 times the index minus 2, minus 1, and without a minus. And essentially, this is the same because I starts at 1. So 3 times 1 minus 2 gives the first element. So it's just sort of, you could do the same thing saying 3 times I minus 1 plus 1, and would be the same thing. But it doesn't matter which way you index it, but essentially looking at the first vector after the multiplus of 3. This is the second one, this is the third one. So now we got all these 3 different variables. So now we can write a simple comparison that says if they are all different, so x1 is different from x2, x2 is different from x3, and x1 is different from x3, then we increment the first value, which was the hand 1. If the first 2 are the same and the second 2 are the same, then that means they're all the same. So we can increment the third one, or otherwise we just increment the middle one, right? So this is very simple iterative algorithm, just looking at a hand at a time and incrementing one of the 3 counts, and then just return the counts. So, looks reasonable. Let's run it just for fun of it, since we already have it here. So here I have the vector, just to prove that it actually works. So this is the same code. So if we go hands version 1 of x, so we're going to get exactly the result. So the counts are just incremented here. So it's good. It's all good. We're just going one by one. The other way to do that, so how could we vectorize this? So the way to vectorize this would be to essentially extract So any ideas how you would vectorize it? What would be the idea? Sort of what would allow us to get rid of the loop? So what do we need to loop for here? Why do we even do the loop? Well, we want to iterate over the different hands, right? So we go hand by hand. So instead of going hand by hand, the idea would be, well, what we can do, we can just extract, let's say, the x1 for everyone, x2 for everyone, and x3 for everyone, and then we can do the comparisons and just sum up the comparisons, right? So instead of looping over the hands and doing it hand by hand, we can just first create a logic saying, well, which is x1, which is x2, which is x3, and then just do a full vector operation on that. So that's what we're going to do. So and this is very common. So the way to do that is usually you constructing an indexing that instead of getting you just the one, which is what we did in the previous example, it will give you the whole lot of them. So in this case, our j that's what's replacing the loop. So we're essentially saying, okay, so let's index all of them. So that means the first ones. So we just get an index that is 1, 4, what is the next one? 7, and so on. So essentially every third one. So that's going to be the first, x1. Then you just need to add 1 to it, and you get the one afterwards, and then the third one. So instead of doing it just for one element at a time inside the loop, we can just do it outside the loop for all of them. So this gives us x1, x2, x3. So now these are vectors. So we can use the same logic we used before in the if statements, but we don't need an if statement. We can the same logic just gives us a vector that says true or false, right? So instead of doing if, this, then add, we're just going to generate a full vector based on every entry. So each hand is one element in those vectors, and that's going to give us a true false for these three options, right? So they correspond exactly to the same conditions that we had in the if statements, except that we had an else in the other one. So now instead of an else, we're just saying, well, if it's not one, well, if it's 1 or 3, then we already covered it. So if we negate that, then we get the third case. So it's just our else statement is now we have to explicitly turn it into a logical or Boolean operation. So once we have all these vectors, all we need to do is just to sum them up, because as we've learned, the sum of a logical vector is just the sum of the truths in there. So that's all we need to do. So this allows us to run this on a large number, and there is no loop involved. And the whole point is we're replacing the loop with this indexing, where we essentially say create a vector instead of doing it one element at a time, right? So again, we can go here. And that's sort of the fundamental. Anytime you have like in the assignment, a question sort of how do you go from a loop to something that uses just vector operations, then this is something you have to do. You have to think, how can I construct something that has all the information I need first, and then I run just some kind of summary on the rest of it. So let's do that here. Then we can prove that the result is truly the same. So we do hands v2, and yes, we get the same result. And for small m, this may be faster because you don't need to create anything big or any intermediate steps. For large m, you would expect this to be faster because you can just generate it all at once. So let's see if that's true. So we're just creating, so the idea, so this is just setting the seed as we talked last time. So let's just draw from binomial distribution. So this essentially gives us just 0, 1, or 2 with a probability of 0.3. So it's not even, but we can look at the distributions. And plus 1 just to make sure it's 1, 2, 3. Doesn't really matter, but to match the example we had earlier. So let's do that, and then we can just run hence the version 2, and we get the result. We see there's more in the middle than the other ones. And we can actually look, there's a function called system.time that gives you the timings for the function that you're calling. So we can do that. for the first one, and we can do it for the second one. So you can see for the first one, it takes about 200 milliseconds, so 0.2 seconds total time. So user time is the time spent in the actual R code. System time is time spent in any system routines where what it really means, normally it should be close to 0, but if you did something like there was a lot of memory swapping around or something like that, that would be sort of accounted for the system and not your program. And elapsed is the real time so literally wall clock sometimes called, essentially says, how long did it take? There's a difference on most machines you will be dealing with. These two will be pretty close, but if you had code that was actually parallelizable and was using parallelization, you could actually incur more user time because you could be using multiple CPUs or multiple cores on a CPU in order to sort of collect more time. So it's not, the user time is not always actual real like lifetime. It can be sort of multiple of the cores or threads that you're using. Anyway, bottom line here is that for the first example, it's 0.2. For the second one, it's about 0.3. So it's significantly faster to use the second version than it is to use the first version. Just one note about system times. Or in general measuring times. It's good to repeat your experiments because there are a bunch of sort of behind the scenes things happening that mean you can actually incur penalty on the first run of a code, especially with the latest R versions. Because what happens is if you use a function, the function actually gets compiled when R figures out that you want to use it more often. And that speeds up subsequent usage of the function. So there's a lot of things behind the scenes. So it's good to repeat it a couple times if you want to measure reliably the time spent in here. And also that gives you an idea of sort of variance, or where are you, how different are the timings over a period of time. So be always, as a statistician, you have to be very careful or very wary if someone gives you just one number, because point estimates are not always very good, as we well know. So just something to be aware of. All right, so in this case, it's a good idea to do the vectorization, especially for large X. Right? If you did that for small X, that wouldn't really matter. So here, this is just showing the results that I was just running interactively. Some useful functions if you're dealing with vectors. So far we've been using summing up logical vectors. Useful. There is a function called which essentially allows you to take a logical vector and figure out which of the elements are true. This is quite useful in many cases, especially in indexing you can use a Boolean indexing, but if you want to work on it further, let's say you want to do subsets of only the sets that you extracted without going back to the data set, you can run it on the indices instead, for example. So there are many other cases where that's useful, but so in this case, when I give it a vector that has true, false, false, true, so it just gives you the locations, so the indices of where the truths are. So it would give you 1, doesn't give you 2, doesn't give you 3, gives you 4, right? So it's the index of where the truths were. The other one is which max and which min. So instead of looking for a maximum and then doing comparison where in the vector was the maximum, the which min and max will give you the index of the first maximum or minimum. If there are multiple, you won't get the other ones. You only get only one. So this is useful if you just want to know the location of the maximum or the minimum. So here in this case, the first maximum, the first 10 here is a fifth position. So that's what you get. You get the index of the first 10. Another one that's quite useful is diff, which essentially takes a vector and gives you the differences between the elements. So it will be always one element shorter than your input, because there are only n-1 differences between the values. So in this case, it goes 3 minus 1 is 2, 6 minus 3 is 3, 4 minus 4 is minus 2. So you get the differences. Very often, again, something that's used a lot, especially in indexing and other things. Sometimes when you're indexing the same, sometimes you want to have the same length, so you may want to think about, usually what happens, you probably want either an additional element in the front or in the back, depending on what the usage is. So a lot of times maybe you want to prepend a 0, so that you're saying, well, before the first element I had a difference of 0, so you would do C of 0, diff, and sort of very often that's used when you're looking at data and trying to figure out, where are the different differences. And here is just, proving that the cumulative sum just gives you the differences between the results of the sum. So it's increasing, right? If you did diff on 1 through 4, it would be just 1, 1, 1. If it's on the cumulative sum, you get 2, 3, 4. Another one that's quite useful is tabulate. So essentially it counts, takes integers, and it finds out how many times did those integers occur. So let's maybe do a simpler example. So if I do tabulate, oops, where am I here? Tabulate of, let's say, 1, 1, 1, 2, 3, 3, then I get 1 3 times, 2 once, 3 2 times. Right, so this gives us the count. There's another one that's sort of more general. So tabulate works on integers. You can also just say table. And what it will do is it will actually, that you can use with non-integers. And so in this case, it has the same result, just gives you the actual numbers on top. But if you had, let's say, instead, let's stay with integers. If I deleted a 2, then table would only give you 1 and the count and 3 in the count. So it wouldn't keep the 2. If you do tabulate, so it will give you the 0 for the 2 because it does the sequential elements. The thing about table is you can use it with any vector. So if I go up, if I do table of, let's say, A and B and C, then it will give me the counts for A, B, and C, and put the names of the vector will be the values that I put in here. So it's not limited to integers, whereas tabulate is limited to integers. Okay, very useful. Maybe because table is so useful, you can actually even do two-dimensional contingency table. So let's say if I have 2 vectors, so let's say I have here x, 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 and y, then it tells me there are 2 cases where I have x's and x and a together. So if I get a and x, I have a and x, so it's 2 of them. Then I have b and x, so b and x occurs once, and c and y occurs once. So I have a contingency table. Very useful if you want to check things. It also works on logicals. So for example, this is often used. So let's say if we do 1, 1, 1, 2, 3, 3, let's say, whatever. So you can also say table, let's say x is bigger than 1. Then you see, yeah, there are 3 numbers that are bigger than 1, and there are 3 numbers that are smaller than 1. So this is, again, very useful for if you're looking at data and trying to understand it. All right, so let's go back here. So we tabulate. You can specify the number of bins. So essentially, as we said, tabulate starts, does a positive integer, so it's 1 through a number. You can normally it's whatever the highest number is will be the end, but you can actually specify how many bins you want. So what's the last bin? And as I said, table useful, but the table goes by just the values that actually occur in the data. So it doesn't treat integers in any special way. It just uses them as entities. So an application here. So let's say we have a sequence of just 0 and 1s, and we want any zeros between the ones, we want to treat them as a gap. So, if we have here 1, 0, 0, 0, 0, and then there is a 1, so we have a gap of 4 here. There's a 1 and there's a 1, so there is no gap, so it's a 0 length gap. There's 1, 0, 0, 1, so there are 2, so it's a 2 length gap. Here is a 0 again, here's a 0 length gap, and nothing here. So that means this is the 4 here, this is 0, this is 2, 0 and 0. So that these results here, what we would expect. Okay. So we want to summarize the result of the gap. So far, these were the actual lengths of the gaps. The question was, can we summarize it? The summarization would be, we want to say, we saw 0 3 times. We never saw a gap of length 1. There was one gap of length 1, and there was one gap of a length 3 or more. So we want to truncate it and say, well, that's the maximum. We don't care about the rest. And this is actually quite useful property to look at the gap in a context of a gap test. So let's implement our gap frequency function here. So how would we go about this? So this is our sequence. We could first we could look at which ones have a 1. In fact, that would allow us to use any value. It doesn't have to be 1, but so first let's go from the numbers to booleans, and you could actually just coerce it to. Would be the same result in this case, but if that was something else, then you could be more flexible. So anyway, so from 0 and 1s we go to false and trues. Then we can ask which ones are true here. So which of x is 1. So that gives you the locations of the ones. Okay, so instead we went from the vector to the indices of the ones. And then if we do the difference between the indices, that gives us the gaps, except that the gap would be 1 for 2 adjacent numbers. So it's not 0, which we looked at before. It's sort of 1 more than the gap as we defined it earlier. So we, instead of saying 4, 0, 2, 0, 0, we're getting 5, 1, 3, 1, 1. But it's up to the 1, it's exactly what we want. Okay? So this allows us to just find out the values, and then we can use tabulate to create the table. So here is going back to the gap. Then if we want to truncate it, then we would say we do a parallel minimum of the gap and our maximum. Now this is a little naughty thing here. You could just do assign 3 to t outside here and then just use the t. In this case, this is just doing the same thing inside. So it's just saying, well, because I will need t later, I'm just doing it here and assigning 3 to it. So really it's just p min of gap comma 3. And so that gives us the gap truncated to 3. And then just doing a tabulate. And now we subtracted the 1 here, but we're just adding it back up because tabulate starts at 1. So the first element will be 1. You could also just not subtract it and so on and just increase the t or something like that. But many ways to do things in R. So that's this, and then we just assign the names. So we're assigning the names 0 up to t minus 1, and the last one we say it's the t plus. So it just as a label. So these are just labels. So now we get exactly the result here: 0, 1, 2, 3 plus. And this is what the function would look like. Now the reason why the t was there, right? When we write a function, we just make it an argument, so we don't need to assign it anymore. So it's just we just remove the assignment here, and we're done. So the code is identical to what we've seen previously, and we just wrap it up into a function that provides the x and t. And just a comment here that this is the same as if you wanted to. The other way you could do that, you could just say, well, for anywhere where a gap is greater than t, you could just set it to t. Maybe one is more readable than the other one, depending on how you see it. But both are fine. So this is how you can package up the code. We can run it just to prove, I suppose, that. Oh no, we can't because I didn't store that one in here. So. Yeah, I don't want to type it all right now, so you have to trust me that it works. So this is just another way that how we can use the point here. The main point of this function was using which and diff essentially looking at indices and then determine, whenever you work with gaps, you probably want to use a which and then diff to just figure out what are the differences between the indices, which gives you the gaps. Very, very useful for other things, like if you wanted to do rung length encoding and on things like that. And here is just an example of running it for large values or large vectors, and we'll give you the counts, the distributions of the gaps. So in this case, the idea is that in order to generate a vector, then you could just draw a uniform sample and then define ones and zeros depending on just some probability. So let's say if it's between 0 and 0.3, then you mark it as a 1, so you get fewer ones than zeros, so that you expect some gaps. So that way you can just generate a vector. So this is just generating a long vector of values between 0 and 1. And then we're saying, okay, if u is less than 0.3, then it's true. So that's actually, it won't give you 0 and 1, actually will give you true and false, which again amounts to the same. And then you can just run the gap frequencies and just specify what's your end threshold, and you will get the results here, just to test it. All right, are we going on time? We have time to start matrices. So now the fun stuff actually comes. With respect to, so far, there was actually a couple of people had a question, what's it with the recycling here? You know, why do we use these recycling rules? Why can you use a smaller vector with a bigger vector? What kind of sense does it make? Well, so far, it didn't really make too much sense, other than with a scalar, right? A scalar did make sense. If you do a long vector times a scalar, you just element-wise multiplication of all the entries. Well, the real reason why we have recycling are matrices. And that's why we get into that now, and why it actually makes sense. So a matrix is essentially just a rectangular arrangement of values which are of the same basic type. Doesn't have to be just numeric, but pretty much 90% or 99% of the time we were talking about numeric matrices, because it's the most useful way to use them normally. So let's talk about numeric matrices. So it's a rectangular arrangement where you have columns and rows, and well, you know them from maths, but it's pretty much just the representation of a matrix as a data structure. And so in this case, we have 2 columns and 3 rows. And the way we call the indexing is always the ij. If I'm indexing a matrix, I'm saying which row it is first, and then I'm saying which column it is. So if I say 1, 1, it's this element. If I say 2, 1, it's this element. If I say 1, 2, then it's this element, right? So that's how you index a matrix in maths and in here as well. The way it works in R is the matrix is essentially just a vector that is logically split into these 2 pieces. So if you look at it, you can see this 1, 2, 3, 4, 5, 6. So really, the way it's actually stored in R, you can treat a matrix as a vector in R, or vice versa, if you tell it what it is. And it will be just column major format, as it's called, which it means it stores the columns first. So it's the first column, then it's the next column, then it's the third column, and so on and so on. So if you were to see it as a vector, so that means just a sequence of n numbers, okay, then this is how the indices would go. Like it would go first element, second, third, fourth, fifth, sixth, and if it was a bigger matrix, it would be 7th, 8th, 9th, and so on. So that's how you can access the elements. Or you can access them as part of a matrix, saying, row and column. So in order to create a matrix in R, what you do, you actually give it the vector of the values, the full vector, and then say how many rows and columns you have. So in this case, we're saying, okay, so let's get the values 1 to 6. So it's a vector of 6 elements, right? And we say, well, really, what I mean is it's a matrix which has 3 rows and 2 columns. You can actually omit the columns because you can infer it from the length of the vector what the number of columns is, or you can omit the rows. So you can omit either, and then it's going to just infer the rest because it knows the length. So here you can see, and the way Matrices are indexed is again through sort of square brackets, and in a vector we just had one value that just told you the index inside the vector. For a matrix, you're just saying row, comma, column. And if I'm not specifying anything, remember we talk about missing values, it means you get the whole thing, which is why these things are labeled the way they are labeled here. So if I say a matrix and then do a bracket, comma, 1, I get this vector. I get the first column. If I say bracket, comma, 2, I get the second vector. And conversely, when I start with the first element, so which is the row, and I said I want the first row, and I'm not specifying the column, then you get these two elements. If I do 2, then I get the second row, and so on. So that's why we have these labels. It's kind of help you to say this is how you would get the row, this is how you would get the column. So it becomes clear what the content is. Technically, if you have data that you want to turn into a matrix, but you actually somehow got the data in a row major format, meaning the vector was such that you would have one row, then the other row, then the next row, you can create a matrix that way as well, and you can say by row equals true. If you create, in this case, that means then you go 1, 2, 3, 4, 5, 6, right? However, the storage is still in row major. In column major. So the way, even if you say by row, it doesn't mean that it changed how the vector is represented. The matrix itself actually will still be stored so that the resulting vector in the matrix will be 1, 3, 5, 2, 4, 6, which is important to note. So this is just sort of a convenience when you're constructing the matrix so that the input can be sort of different, but the actual way it will be stored will be still the same way. And that means we can always, this is, major difference from Python where you have to worry about these things all the time, and it's almost impossible to write code for it because you can never know how a matrix is stored. So here it's always stored in the same way, so you can always rely on the way to access the elements by index. So, for the first argument to the matrix function, so you're just calling a function really, as everything in R, is the actual content that you want to create the matrix from, and then you just give it the size. If you just specify, recycling rules for the content apply as well, so you can just create a matrix saying 1, comma, and then just give it the columns and rows, and it will create a matrix with that content. So in this case, you cannot omit, rows and columns because you have to give it. It cannot be inferred from the length, but you can create matrix this way. And this is what I already mentioned, that if you can omit one or the other if it has to be inferred from the length of the vector you're providing. The way, so if you look, so let's go back to R and to talk about this one. So we have created a matrix. So let's say with I forget what we did, 3 rows. So I don't have to name the argument, but it was named so that it's specific. Well, actually, not to 16, to 6, right? So as you can see, it was actually creating. Oh, let's actually go back since I already did the mistake, right? So it actually is warning you that I did specify. I really meant 6, but I typed 16. So now I have 16 elements, but I have 3 columns. So it's 16 is not divisible by 3. So it's saying, but hold on, I'm going to recycle, but do you know what you're doing? So, you don't actually get an error, but you get a warning. And you can, as you can see, it gets recycled, where here the last 2 elements get added from the beginning because that's the recycling rule, just to make sure that it has the full size of the matrix, but it's warning me, which is good because I didn't actually intend to do that. So now I have the matrix I was actually talking about. So you can ask about the number of rows. You can ask about the number of columns if you have a matrix. And there's a concept of dimension, which is general. It's not just limited to matrices. It's actually, you can extend that to arbitrary many dimensions. So you ask what are the dimensions of M, it will give you a vector that has the number of rows and number of columns. And if you have a multi-dimensional array, which we may mention later, you would have all the dimensions if it carried on to like X, Y, Z, and so on and so on. So for a matrix, you get the number of rows and number of columns as in using this dimension as the dimension information. That's what's often called. And let's see if I do a structure. So if I do a structure of M, it will tell me this is an integer matrix and has essentially shows you the indexing. So it says there's 3 rows and 2 columns, and that's the content of the actual vector. So here you actually see the vector in the way it's actually in there. So as an example of what I was saying earlier, when we said if I say by row equals true, okay, so then we get our matrix that is 1, 2, 3, 4, 5, 6. And if I look at what it looks like, it's now 1, 3, 5, 2, 4, 6, as I was saying. So it goes this way and this way. All right. You can construct, so far we were able to create one matrix. Very often you may want to construct matrices from either vectors or by combining other matrices. The 2 matrix functions to do that, and they again are generic, so they work not only for matrices but other rectangular objects, are cbind and rbind. What C stands for column bind and R for row bind. So what it really means is binding together the things you give it, treating them as columns if it's C or as rows when it's R. So in the first example here, I have one vector 1 through 1 to 3. The other one is 4, 5, 6. And if I say cbind, it says I want to treat them as columns and I want to bind them together into a matrix. So each of them will be one column in the matrix. So I'm getting this result. If I do rbind, I'm binding them as rows. So then I get 1 through 3 is going to be 1 row, and 4 through 6 is going to be the second row. Very useful if you want to have sort of a readable, if you want to construct a matrix in a more readable way, then, well, one way is just you indent things in the editor. So if I'm constructing a matrix from scratch, let's say, so here I can say, okay, matrix of, and then I can say 1, 2, 3, comma 4, 5, 6. So we want 2 rows, and by row, let's say. So this way I can sort of see it visually what the matrix looks like. Whereas if it's just in 1 row, it's how much harder. So that's one way. The other way, you can just say rbind of C 1, 2, 3 and 4, 5, 6. That saves you specifying columns and rows and things like that. So let's just run these 2 just to make sure that they actually do what I was claiming they do. So you can see we have 1, 2, 3, 4, 5, 6. If I do the rbind, I get the same thing, 1, 2, 3, 4, 5, 6. And it's more readable in the script so that you can actually see the form of the matrix. Again, they don't have to be the same length. So similar recycling rules as earlier. If something's missing, then it will be recycled to fill up the matrix that it would generate. Some more complex objects, actually, it can even give you errors if you, let's say, try to combine things that really are incompatible. But for matrices, it will just do the binding and produce a warning if the one is not the multiple of the other. The next step is, so far we dealt with just matrices, which is fine, but very often what you're getting, and if you recall, let's say when we did a contingency table, right? So we had ABC on the one side, XYZ on the other side. So it's very often quite useful to have names associated with the columns or rows. You can think of things like if you had a data set, maybe you would want the columns to have the name of the variable. If you were to combine it into matrix. So there's very many use cases for names, named objects. So, and as you recall, for vectors, we already had names. We could just say names of a vector and assign it certain strings or character vector and use it that way. The same thing applies to matrices. So we can have row names and column names. So row names and col. Col names are the two functions. They're how you can access the names of the rows and the columns, and you can just set them. And just in the same way that we had columns, number of columns and number of rows, and then there was the function called dim for the dimensions. We have dim names, which gives us the names of the dimensions, which are just two vectors, two of the name vectors with the names. So if we do that, so let's say do I still have some M here? So I do have M. So I can say, let's say row names of M are A, B, C. So I have 3 rows, so I need 3. If I look at it, now I can see A, B, C here on the side. If I say column names of M equals X, Y, so I just assign the two names, and I can look at M, and now I see X, Y, columns A, B, C in the rows. So now if I say dim names of M, I'm getting a list. So previously, if you recall when you did dim, or let's do dim actually, since we're at it, you get a vector of length 2, where the first one is the number of columns, the second one is the number of rows. First one is the number of rows, the second one is the number of columns. When you do dim names, you have again a vector, in this case a generic vector, aka a list, with 2 elements. The first one are the names of the rows, and the second element are the names of the columns. So that way, and you can specify this when you're creating a matrix, so you can kind of do that, or you can set them directly, both of them, if you want to send them both at the same time. So this is quite useful. So this is what we just referred to: row names, column names, and dim names. Indexing in a matrix, I briefly mentioned that when we are going over the matrices, is done again by brackets, angled brackets, where you do refer to the row first and then the column. So if you want to iterate over, this is highly inefficient, but if you wanted to do a sum of all the elements of a matrix, you could iterate by setting I from 1 to number of rows of X, J 1 number of rows of X, columns of X, and then just add up the numbers. Because matrices are just vectors, you can just simply say sum of X and you're done. So a lot of times there's a lot of operations that you can simply, if you think of the matrix as a vector, they're much easier. So for example, and then now we go back to the recycling rules. So I won't probably stop here in principle, but the recycling rule, so if we go back to the matrix here, right? So we said this is just a vector that's stored like this, right? What this means is if I multiply it with a vector of length 3, it's essentially just a row-wise multiplication, because now it makes sense, right? Now it makes sense if I multiply with something that's of the size 3, I'm just multiplying this with the first element, this with the second element, this with the third, this again with the first, with the second, and the third. So now all these operations actually make sense. So the reason for the recycling is for actually these sort of special cases. So for a scalar, so if you have just a vector of the length 1, you're essentially just doing scalar multiplication of all the elements in the matrix. If you do a division, it's just a scalar division of, and so on and so on. If you do a multiplication vector of the same length as the rows, and this is important, this must be the rows, then it again makes a lot of sense, right? So that's the main reason why we've been sort of, bashing on the recycling all the times, because it just makes it so much easier to write down things. And if you want to multiply something by column, how would you do that? Any ideas? There's one more operator actually I should show. How would you do that if you had a vector and you wanted that to be sort of a column multiplication? What can you do to do that? Any ideas? Or is it too late already? Yes, it's too late. All right, so you can transpose the matrix. So you can just say T of M. So this was our M. If I do T of M, I'm just going to transpose the matrix. So now my rows, my columns turn to, where am I? My rows turned into columns, so now I can just multiply by something that's of the length 2, and now it will work. So it's just like the multiplication. So it will be just transpose M, do the multiplication, and then you can transpose it back if you want the original structure. So that's one way to do that, but allows you to do both ways. All right, so that was matrices, and so have a great weekend, and see you next week. Actually, some of you I will see later on in the labs.
Why does the recycling rule work while